So let's start here. This is slide 20. And we've talked generally so far about correlated data. Correlation can happen in a variety of ways. One way, commonly encountered in biostatistics applications, is longitudinal data, where you are observing the same individual over time. And that's a handy design if you are specifically interested in seeing how things change over time. What is your level of pain over the course of a treatment regimen? Does the drug work well in dropping pain initially, but it comes back up after 6 months? Or does it drop down and stay flat? Or what? What is the temporal pattern of a treatment, say? So a little bit of notation. Let's say that our model is this. It's a regression model. Yi, that's the collection of observations on individual I. So like in the orthodont data, we have 27 individuals. I would have Y1 for individual 1. And for that individual, I have some number of observations on the same individual. In the orthodont data, we had 4 observations on the same individual. So for Y1, I would have Y1 at time point 1, Y1 at time point 2, 3, 4. Yij, we're going to say, is the response for individual I at time Tij, whatever time it was that corresponds to. In the orthodont data, every individual was observed at the same 4 time points. But more generally, we could have n individuals and they could all be observed at different time points, and maybe different numbers of time points. There could be different numbers of observations per individual. So this is kind of a general way to set up a time course data set. Also for each individual, I have their covariates, which generally could be represented as a little model matrix or a design matrix. Because at time point 1, what was your disability insurance status, say? What was it at time point 2? What was it at time point 3? Well, maybe halfway through the study you went on disability. Covariates can be unique to each time point. So we could represent your covariates in a matrix way, 1 row per time point, and then for each covariate I have a column. In the orthodont data set, we might say there's a 4 by 2 design matrix for each individual. First row tells me their age, or the first column tells me their age. Second column tells me their gender. So the second column is not changing in that example. They're always female, they're always male, but that first column is changing across time. So you can have things changing over time. According to our model, we're going to say that the mean is equal to something, some mean vector, mu I, and the variance covariance is equal to something, call it sigma. So this is where we are allowing for correlation between repeat observations on the same individual. But backing up to the top of the slide, we're just doing regression. I want to say mean orthodontal distance equals beta 0 plus beta 1 gender plus beta 2 age plus beta 3 interaction. And let's do inference on age. And let's do inference on gender, maybe. So I want to estimate the coefficients of the model, and I want to get standard errors for those estimates. It's just a regression model. But we have to be careful now because there is this correlation. Okay, so whenever you use software to do correlated data analysis, correlated data regression, often you'll be given a choice of a handful of named correlation structures. This is because if we're going to do correlated data regression, we have to deal with this capital sigma thing. And one way to deal with it, like in this weighted least squares example that we talked about, GLS needs to estimate sigma because that's what it uses to do all the estimation and standard error calculations. So it needs an estimate of sigma. How can you estimate sigma? One way to do it would be to just completely say nothing about how it looks and just allow every component of it to be estimated separately. So that would be the totally generic way to represent sigma. Everybody is allowed to have their own residual variance, and everybody's allowed to have their own unique pairwise correlation. That actually has a name. That's the unstructured structure, where, well, actually I do have some structure here because I'm saying everybody has the same variance. But it's unstructured in the sense that everybody's allowed to have their own correlation between pairs. So the first individual or the first time point has a correlation with the second time point, but there's maybe a different correlation between the first time point and the third time point, second with the fourth. All of those are allowed to be different. So if you had a huge sample size, maybe that's the right choice all the time. That way you're really not making any claims or assumptions. You're just allowing for the data to determine what the correlation looks like. It does require a large sample size usually because you're, instead of one little sigma squared in the OLS case, you now have little sigma squared in all those correlations. All the pairwise correlations have to be estimated. So that uses up degrees of freedom. The more parameters you have to estimate, the smaller your power is going to be to test something. So you would prefer if you could say, if you could limit what the correlation looks like. And like in the paired example, we were able to do that. If I'm doing a paired design, I know what the correlation structure is. Let's say we're comfortable assuming constant variance, and we have n individuals under the control group, followed by the same individuals ordered in the same way in the treatment group. This is the correlation structure. There's independence in that in the control group, because that was a random sample. There's independence in the treatment group, because that's the same random sample. But there is some correlation whenever you get to a pair. And so we wrote that out last time. There's one value of rho. There's one correlation that we're assuming applies to every pair. That, quote, structure only has two parameters that have to be estimated, little sigma squared and rho. Instead of little sigma squared in all possible pairwise rows, there's only two. So it's an efficient way to represent the data. I don't use up too many degrees of freedom dealing with it. So if I knew something like that, it would be nice to be able to pass that along to the algorithm, like GLS, and be efficient in the way that things are estimated. Here's a couple of other widely used structures. One is called compound symmetric, and we have seen this one before as well. Compound symmetric looks like this. So the covariance, everybody we're assuming has the same variance right now, and every pairwise correlation, every pair of observations has correlation equal to rho. So everybody is correlated in the same way with little correlation equal to rho. That's called compound symmetric. So compound symmetry looks like the covariance between any pair of observations on the same individual is equal to rho times sigma squared. So let me emphasize that. Time course data, like the orthodont data, we have 27 individuals. I don't want there to be, I don't need any correlation estimated between individuals, because this was a random sample of 27 people. The only place I think there's correlation is within the same observations on one individual. So when I go to GLS and it asks me what's your quote correlation structure, I might say compound symmetric, and what I mean by that is within one individual, I think this is the correlation. I think there's sigma squared down the diagonal, or the covariance matrix has sigma squared down the diagonal, and every off diagonal is equal to this rho sigma squared. There's only two parameters that need to be estimated for that. Common pairwise correlation within the same individual. Another alternative that arguably makes sense a lot of the time in time course and or spatial applications is one where we allow for the correlation to be strongest for time points that are closest to each other, or for locations that are closest to each other, but then to tail off the further away you get. So my blood pressure right now would be highly correlated with my blood pressure 5 minutes from now, but maybe not so correlated with my blood pressure next week. So if you were wanting to have some kind of like tailing off effect of the correlation, this last one is a good choice. It's called AR1, or first order autoregressive. It says that the covariance between two observations on the same individual in a time course setting is equal to rho, so there is just one rho, but we modify it by raising it to the power of the absolute difference in the time points. So if Tij and Tij dash or prime are really close to each other, then the correlation is allowed to be closest to its true value. But as those two get further and further away, you're raising a number between -1 and 1 to a higher power, and it shrinks it down closer to 0. So this has the effect of strongest correlation when you're talking about nearby time points, and then that tails off the further away you get. Is what correlation? The common pairwise correlation is, it can be two-class correlation. It doesn't have to be. It could be a one-class problem where you're taking blood pressure, and you, instead of taking 30 people from the group you're interested in and taking their blood pressure, you take my blood pressure 30 times. Then there's common pairwise correlation within that one class. There could also be a two-class problem where you do something like that. You take my blood pressure 30 times, and you take your blood pressure 30 times, and let's compare us. Now there's correlation in my group, and there's correlation in your group. So think of these structures as just specifying wherever the correlation is, this is what it looks like. It could be within one class. It could be between two classes. It could be a one-class problem. It could be a multi-class problem. Like in the regression setting, this is, generally multi-class problem. There's different genders, there's different times, and stuff like that. Whenever you do a correlated data regression, like with GLS, you tell it something just like you would in LM. You say, my response is this, tilde, covariance. The other pieces that you have to tell it are, where are the correlated observations? Who's correlated with who? In my 108 by whatever matrix, which of those, which rows come from the same individual? So you have to tell it some grouping variable. So here's my variable. In our case, it would be those M01 and F07 and stuff like that, the indicators for the individuals. I tell GLS that, and now it knows these 4 rows are one person, and those 4 rows are one person. And then the next thing I have to tell it is, what is this structure? So I've told it where the correlation is, and then with the structure stuff, I tell it what the correlation I expect looks like. So that's a general framework. We need to know where the correlation is, and then we can make a guess on what it looks like. So compound symmetric and unstructured and the autoregressive. The difference is unstructured and compound. Okay, so the difference here is that every pair of observations, like in the orthodont data set, we have 4 time points. Unstructured would say time point 1 has correlation row has one particular correlation with time point 2. Write that down. That's one number that we had to estimate. It also has a different number potentially that is the correlation between time point 1 and time point 3. And there's a different one for 1 and 4. And there's a different one for 2 and 3, and 2 and 4, and 3 and 4. So all of those numbers had to be separately estimated. That's why we have this subscript j prime. There is a correlation for 1 with 2, 1 with 3, 1 with 4, 2 with 3, 2 with 4, 3 with 4. All those had to be estimated. In compound symmetric structure, there's no subscript, which means we're saying every pair has the same correlation. Time point 1 is correlated with time point 2 according to row. Same exact correlation between time point 1 and time point 3, time point 1 and 4, all of them. So you cut down a lot on the number of parameters that had to be estimated. Unstructured is, if you had a big enough sample size every time, arguably what you would want to do, because you didn't have to make any assumptions or any claims. Everything's allowed to have its own correlation. It's just that that's a lot of extra parameters that had to be estimated, especially if there's a lot of time points. Okay, we have an example, and then we're going to talk about regression. I'd like to get through GEE. Let's introduce this example, and then let me show you code that you could reference while you're doing the homework. So here's an example of correlated data. These are mothers from Georgia who had 5 children. Every one of our individuals had 5 children. And for each child, we have the weight at the time of birth. Question is, how do the weights at birth change from firstborn to second to third, fourth, fifth? So you might be concerned, for example, that the more children you have, the weight decreases for whatever reason. You know, your motherly resources are used up somehow. So let's think about a time course problem where for each individual I have 5 events, and I have a response value, which is the weight of the child at birth, and what's the time course? How did things change from birth 1 to 2 to 3 to 4 to 5? As an aside, there is a simple way to do time course analysis that doesn't require GLS/GEE. And it's very limited, but in a pinch, maybe it's an option. That would be if I specifically wanted to ask, does birth weight change with birth order? I could just look at the 5th birth and compare it to the 1st birth. So I have for each individual, I have birth weight for the firstborn, birth weight for the 5th born. I could take the difference and do a one-sample t-test, which is the same thing as doing a paired t-test on those 2. I didn't have to do any regression. There's no correlation structure to think about. Very simple. Limitation there is that you just threw away a lot of your data because you had time points, or you had data on the 2nd, 3rd, 4th. So temporal time course data allows you to look more generally at trends, like patterns. You also threw away the ability to adjust for covariates. t-test, you don't adjust for age and race and all those types of things. So if we could do it in a regression context, but account for the correlation, that would be better, more generally. Okay, so in the last couple of minutes, let's just pull up the script for these data. These data are called GA babies here. GA babies. Let's save that. And let's get the script. So here's the data. Let's read it in and have a look at it. So we have several variables. Here, like the orthodont data, we have multiple rows for the same individual. And in these data, the first column is an identifier for which mom we're talking about. So everywhere I see 39, that's one mom. That's the first row is the first birth for mom 1, or 39, 2, 3, 4, 5. So I have a separate row for each birth. Here's mom's age at the time of birth, 15, wow. Up to 25. I don't remember what that one is. Time between each birth in years, okay. An indicator variable for whether the birth weight fell below some threshold that they use to say that's, quote, low. The actual birth weight, so our response variable. And a couple of other things. For our purposes, we're mostly interested in what birth order was it, what number was it, maybe what's the mom's age, and what was the birth weight. This code does the paired t-test. So I'm not going to go through that. It's just pull out first and the fifth and do a two-sample t-test, or a paired t-test. Here's an example of GEE. Okay, so you're going to use this in your homework, and it looks a lot like GLS. So I have examples of both GEE and GLS here. Both of them expect the same information. First, tell me your model. In our case, let's do birth weight response is a function of birth order, and let's do initial age. When did you start having the children? So I want to fit that regression model. The other piece of the puzzle is where's the correlation and what's the structure of the correlation. So for GEE, there's an argument called ID, and that needs to be a variable that tells that's the same, takes the same value for all rows that correspond to the same individual. In our case, that's mom ID. So I'm going to pass mom ID as, quote, ID, and GEE will now know those 5 rows came from the same mom. And then the next 5 rows came from a different mom, and so on. And then the other thing I have to say is, once we identify the observations on the same individual, what do you think the correlation looks like in there? So in our case, we're talking about a 5x5 covariance matrix. And what do I think that correlation structure looks like? If I library in GEE, probably going to have to install it. There's two packages that implement GEE. We're going to use both of them, GEE and GEE pack. Let's library in GEE. The main function is called GEE. So you specify a formula just like in LM. You have to tell it where are the individuals, so give it an ID variable, and then you have to tell it what's the correlation look like, or it's going to make an assumption for you. By default, it assumes no correlation. So if that's your case, you might as well just do LM. Your choices are listed down here under the documentation for that argument. So there's independence, which again, just do LM. There is exchangeable, so we've defined exchangeable. That's every pair of observations on the same individual is allowed to have its own correlation. When GEE says ARM, it's the same thing that we called AR1. It's that autoregressive. No, I'm sorry, I'm wrong. Exchangeable is another, unstructured is what we called unstructured. Exchangeable is another word for a different name for what we called compound symmetric. So exchangeable is the same thing as compound symmetric. And that's what we're going to do in this code. We're out of time, but that's what this code is doing. So it's doing a compound symmetric correlation based on GEE and doing compound symmetric with GLS. So GLS has a similar, has the same needs, but the syntax is a little bit different. Tell me your model, and then tell me where the correlation is and the structure of it in one command. And this is more complicated. I like GEE better, but you can mimic this code, adapt it to your example. This code right here says I want compound symmetric, and that's where the correlation is. All right, we will do this example, we will finish this example in class on Friday, and I will tell you more details about what GEE is. GLS, just weighted regression. GEE is kind of a different animal. It's more general, and it's better, and we'll talk about why. Then the other thing we'll talk about is both GEE and GLS are what are called, quote, marginal models. Everything we've done with regression is a marginal model. And it's to be distinguished from what's called a conditional model, of which random effects are an example. You can also do correlated data regression with random effects. So maybe you've heard of random effects, maybe even used them. We'll talk about them in some detail. They can also be used. They're a little more difficult to interpret, but they are kind of widely used depending on who's doing it. So we'll talk about distinguishing those two techniques. All right. See you Friday.